My name is JunWei, and it's a great honor to share my research with you at the Virus Bulletin. Analyzing Android malware is challenging, especially when it comes to understanding its C2 commands, which often require significant time to identify its location. So today, I'm going to share a new method to speed up this process. I will show you how we can ultimately pinpoint the functions that handle C2 commands by analyzing common core patterns. A little about me. I'm a senior malware researcher at the Record Future, where I do malware analysis and help the Triax Sandbox team catch all kinds of malware. I'm also a volunteer for PyCon Taiwan, and I'm passionate about giving back to the open source community. Here is a journey we will take today. We will start by exploring why C2 commands are so critical. Then I will share some code patterns that the malware author used to handle their C2 commands. The third is to show you how we turn these discoveries into an open source tool, which can help you pinpoint where the function may contain the potential C2 commands. And finally, we will wrap up by looking at what is next and some ideas for future work. By the end of this talk, you will have a new perspective on C2 command analysis. Let's begin with the introduction. The Android malware landscape is constantly evolving. We see new techniques for stealing users' data and new targets every day. But despite all these changes, one thing stays the same. They all rely on the C2 server. And the C2 commands are like the brain of any sophisticated malware. They are the instructions sent by the malware author that tell the malware what to do, such as stealing credentials, encrypting files, or performing other malicious behaviors. Therefore, understanding these commands is crucial to understanding the malware's true capabilities. So, why do we put so much effort into finding these commands? First, they tell us about the malware's core functionalities, from what data it targets to the specific malicious actions it performs. The list of the command is basically a feature list of the threat. And second, they are the key indicators for classifying different malware families and understanding how they communicated with the C2 server. However, finding these commands is not always straightforward. Static analysis has some bottleneck, and many of you here are analysts, and you know that manual reverse engineer is highly time-consuming. On the other hand, dynamic analysis it often fails when deal with the encrypting or obfuscated traffic, or when the C2 is down at the time of analysis. And furthermore, we can't always trigger all functionalities in a sandbox environment, which means many C2 may never be found. So, this brings us to the key question for today's talk. First, how can we quickly locate the function response for handling the C2 commands? And second, how can we uncover all potential C2 commands? And third, is there a way to identify unknown malware in the wild? To answer these questions, we need to shift our perspective. So rather than chasing the ever-changing things, which means the C2 command strings, we focus on more stable architecture, which means the code structure that processes the C2 command. And that is where the C2 command handling pattern comes into play. Moving on, let's now dive into some C2 command pattern we discovered. So what exactly is a C2 commands handling pattern? Let's look at this code. This if-else statement is the most classic way malware author handle their C2 commands. It doesn't matter if the command is get NS or upload file. The logic is always the same. It compares a string and then execute an action. This repeating structure is the first pattern we are looking for. By analyzing many malware families, we have identified 4 primary patterns. First, the class C we just saw, which we can call conditional jumps, with if-else or switch statement. Second is dictionary mapping, which use a HashMap to link the commands and the functions. And third is the array base, which stores commands in a large array. And finally, constant definition, where commands are defined as multiple constant strings in a class. Now let's look at each of these patterns with real-world malware families. Our first pattern is the if-else and switch case structure. It is categorized by a high density of string comparison, which utilize the Android API, string.equal, along with a few frequent Smali opcode, including constant string, invoke virtual, move resolve, and if ukz. And at least one opcode sparse switch, which means it is using a switch statement. On this slide, you can see a decompiled snap from tgtaxi. It is a huge function with a total of 94 C2 commands. And notice the repeat use of the Android API, string.equal, within many if statements in a large switch statement to compare each different C2 command received from the C2 server. And here is the Smali opcode of the previous Java code. Our goal is to find the return in the code. As you can see here, we see constant string to load the command, invoke virtual to call the string.equal, and save the result using move result, and if ukz for checking the result. These 4 lines appear again and again. It is like a repeating DNA sequence. And yes, it is not a coincidence, it is a pattern. And it is actually the bytecode level fingerprint we are hunting for. And you will find similar repeating pattern in the following session that I will show you later. Next, the second pattern uses a HashMap. Here, the malware author maps command strings directly to the functional module. It is a cleaner coding practice, but it still leaves a distinct structure pattern. We saw this in the Xloader, also known as Mocow. It is an Android banking Trojan. The characteristic of this pattern usually have a high-frequency API, which is the HashMap.put, along with a few frequent Smali opcode, constant string, new instance, and invoke virtual. And most importantly, we look for at least one opcode, iGetObject, which is typically used to retrieve the HashMap instance from another object for later use. This code from Xloader clearly shows the pattern. A HashMap is initialized, and the Android API HashMap.put is called rapidly to link it with 20 different C2 commands and their corresponding handler object. On the left-hand side, you can see a series of HashMap.put. Each code associates a command string with a new instance of the J class. The second parameter, a number like 4, is parsed to the J class constructor, which is an index to retrieve the actual handler logic that executes a specific malicious behavior. At the Smali level, the pattern is just as clear. We see a repeating sequence of constant string to load a command string, creating a new handler object, use new instance, and then invoke virtual to call the HashMap.put. Again, it is the high frequency of this particular API code, along with the use of a specific Smali opcode within a function that acts as our pattern. Our third pattern involves storing command string in a large array. The malware typically iterates through this array or use index to retrieve and process the commands. An example of this is the Capybara banking Trojan. The characteristics of this pattern include the frequent use of Smali opcode, such as constant string, output object, And most importantly, we look for at least one specific object code, new array, which is used to initialize an array for adding new elements later on. As you can see in this code snap of the capybara, the malware initialized a string array and defined it with 59 different command strings. And this large static array of strings is a huge red flag for the malware analyst. The Smali object code reflects this perfectly. You will find that this kind of C2 command pattern starts with the object code new array to create an array for data use, and then a high concentration of constant string object code followed by output object, its main array put, which places the string into the array. A function containing thousands of these sequences is likely to be related to the C2 command definition. The fourth and final pattern is a bit different. Instead of a single function, the pattern is divided within a single class. The malware author defined a large number of C2 commands as constant string, either as static field or instance fields. And there is a frequent usage of the Smali object code for constant string and output object. We will use a malware family called Nexus as our example. Let's first look at a static field subpattern found in the Nexus Trojan. This class is essentially a dictionary of constants. It contains 39 static string variables, each representing a C2 command. In Smali, this translates to a class file with a high number of output objects, its main static put object code in its class initialize method. Each output object is used to assign a value to a static field. Another is the instance field subpattern. Here, there are many strings defined as an instance variable. We found this in the Cerberus banking Trojan. In this variant, it's used RC4 encryption with base64 encoding for this string. The characteristics of this pattern include a high usage of Smali object code, such as constant string, invoke virtual, move result object, and output object. It typically indicates that a load string function code to decrypt it or decode strings, and save the result into various instance fields. This code from Cerberus shows a class where many string variables are declared as instance field and initialized within the constructor. And at the Smali level, the fingerprint is a high concentration of output object. It means instance put object code inside the constructor method. As you can see here, it first uses constant string to load the encrypting string, use invoke virtual to call the decrypting routine, and save the result via the move result object, and then use output object to set instance fields. Now that we have identified this pattern, how can we automate the detection process? So let's now move on to our methodology. We propose a lightweight static analysis method to identify this pattern directly from the Smali object code. And the process is simple. First, we pass the Smali object code from a disassembled APK or DEX file. And second, for each function, we count the occurrence of a specific Smali object codes and the Android API codes that are characteristic of the patterns we discussed earlier. And finally, we apply a set of rules with predefined threshold. If the counts within a function meet or exceeds our threshold, we flag it as a potential C2 command function and extract all the string within it. Let's make this more concrete with an example rule for our first pattern. which is the if-else switch pattern. We look for a combination of key opcode, sparse switch, constant string, invoke virtual, move resource, and if equals z. And the corresponding Android API for this pattern is string.equal. Then we set a threshold of 10, for example. Here, this is representing the minimum number of C2 commands required to flag a function. This conservative number is based on our analysis of various malware families, as most C2 handler contain far more than 10 commands. Of course, you can adjust this threshold based on your own findings. Here is an example of our rule. We define this rule in a simple JSON format, which makes the detection engine flexible and extensible. As you can see, a rule defined the target opcode, the API to look for, and the threshold count. It allows us to easily add new rule for new pattern we discover in the future. Finally, when the functions match a specific rule, the tool output the function name. And in Java, it is called the method signature. And then we will extract all the strings within that function. This process is entirely static, which makes it faster than the dynamic approach. Here is what it looks like in practice. The complete code of the implementation is open source on GitHub. It is called C2Hang. And you can give it a try if you are interested. When running the C2Hang from the command line, you can use the option F to point it to APK or DEX file. And you can specify your rule when the option O. It is designed to be simple and integrate easily into the automated analyst pipeline. Here is an analyst resource of the TG Taxi malware by our tool. You can experience the power of the C2Hang. After executing the command, it quickly tells us the C2 commands are located in this specific function. And even better, it extracts all the potential C2 commands for us, such as screen relay, read SNS list, and so on. So what used to take hours or even days of manual work can now be complete in just a few seconds. So C2Hang works on the plain text commands, but what about the encrypting ones? Here is a resource of the pattern number 4 of the Cerberus malware, where there are many encrypting-like strings, and our tool flagged this constructor method. It's then extract all the string within it, which are clearly encrypted. And for a malware analyst, this is the red flag of something valuable here. So instead of searching through the entire application, our tool tells you exactly where to look. Your next step is now clear, reverse engineer this specific class to find the decryption routine. And of course, no tool is perfect because C2Hang looks for the structure pattern. It can sometimes produce the false positives, such as flagging the functions that do not contain the C2 commands. Our goal is to take an analyst from searching through thousands of functions down to investigating just a handful of highly suspicious candidates. It is a strategy trade-off between efficiency and precision. And it is helpful for malware analysts when dealing with such complex Android malware. Now, let's go back to the 3 questions we asked at the beginning and see how our approach answered them. Our solution focuses on matching the C2 command core pattern, not specific strings or APIs, and this allows us to build a scalable detection mechanism. This slide visually shows the answer to the question 1 and 2. As you can see, it is the exact function identified by the C2 hung. And without a tool like this, you could spend entire days looking through each class. However, with the C2 hung, which speed out this process, you can save valuable time. So right now, we have narrowed our focus to the specific area of interest within the entire file. This research also answered the third question: how do we identify an unknown malware in the wild? First, if a sample C2 command structure is clear but doesn't match our database, it is a strong indication that we have found a new unknown malware. And second, by comparing the C2 commands with our database, we can quickly confirm if a sample is a new version of an existing family. For example, our tool helped us identify a new TG-Taxi variant last year with a higher number of the C2 commands than the original version. All right, so let's get to the conclusion and the future work. In conclusion, we have presented a scalable and family-independent mechanism for detecting the C2 command handling patterns. Our core philosophy is that the malware author can easily change a command's name, but it is much harder to change the core architecture that processes those commands fundamentally. And this research proves that by analyzing the control flow at the Smali level, we can understand a malware's true capability more effectively and rapidly. And looking ahead, we plan to expand our rule set to cover more malware families and different types of C2 command handling patterns. We also aim to enhance the rule engine to support the API cross-reference for more complex pattern detection. And most importantly, we want to automate it and optimize the threshold. And as you already know, the current threshold is fixed, but in the future, it could be dynamically adjustable to improve the performance and the precision. And that's all for my presentation. Thank you all so much.